Hi, welcome to part 2 of electromagnetic induction. Here I am going to teach you how to apply Lenz's law to predict the direction of current. So this is for students who have already gone through part 1 of electromagnetic induction. I have explained clearly the concepts of Lenz's law in part 1. So only those who have gone through part 1 can proceed through this video. Otherwise, you can stop here and go to part 1 and come back to this video. Here we have two magnets, two bar magnets. This one on the left and one on the right of this loop which has a capacitor. A and B are two plates of the capacitor. Here we need to predict the polarity of the capacitor plates A and B. As we move the bar magnets 1 and 2 towards the loop. So we break the question into two parts and we come to this bar magnet which is on the left side of the loop and we move it towards the coil. And we move it towards the coil which has the capacitor plates A and B. Now, once we we look at the coil very clearly. Just look at the coil very clearly because it's a 3D concept which you need to understand. Once you have dotted lines on this side, this means that A and B, if you look at the plates, capacitor plates A and B of the loop from towards the side of the magnet, they fall on your left hand side. Exactly like this. They fall on your left hand side. I give you 5 minutes to see clearly, carefully how these capacitor plates, when you look at these from the side of the magnet, they fall on the left hand side. Your eyes are here. Your eyes are here. So you're looking at the loop from the left hand side, that is from towards the side of the bar magnet, and the capacitor plates, they appear to be on the left hand side, on your left hand side. Since the north polarity of the bar magnet is approaching this loop, the loop from on the side of the magnet will develop a north polarity, and hence the current in the loop should be anti-clockwise. Now, as I said, if you look at the loop from the left hand side, the capacitor plates appear on your left hand side, So they look exactly like this. If you draw the loop on the plane of the paper, it looks like this. And the current is, since it has to develop a north polarity, you could draw the anti-clockwise direction. You can put an anti-clockwise direction to the current. And you see that the current is coming out of plate B. So as the current keeps flowing through the capacitor, the positive charges are stuck on this plate and negative charges are stuck on plate B. So A is more positive with respect to plate B. Now we come to the other part. In this part, the bar magnet which is on the right side is moved towards the loop. It's moved towards the loop. Again, it's a 3D concept. It's a 3D concept. If we have dotted lines extending from the center, you understand that AB is on the, when you look at the loop from the side of the magnet, your eyes are here, you're looking at the loop from the side of the magnet, you see that AB, the capacitor plates, are on your right hand side. So you can draw this on the plane of the paper with the capacitor plates on the right hand side of the loop. So since the south polarity is approaching the loop should also develop a south polarity to repel the magnet. So the loop should also develop a south polarity to repel the bar magnet. This is as per Lenz's law. So now since it is a south polarity, the current direction is going to be clockwise. So here we mark an arrow showing the clockwise direction. So again we see that the current is coming out of plate B, and as the current keeps flowing, positive charges are stuck on plate A and negative charges on plate B. Hence A is again more positive with respect to B. We come to another question. Here we have a loop. We have a loop here and a current carrying coil. This is the loop and this is the current carrying coil. So what happens once the tapping key is just closed? So we close the key. So current starts flowing in this direction from the positive side of the battery. It starts flowing. Now what we need to predict the direction of current in this loop. So the question is, we need to predict the direction of current in the loop. So when current starts flowing through this coil, if we look at this, if we look at the coil from the side of the loop, we realize that the current is flowing in the clockwise direction. So this coil develops a south polarity. It develops a south polarity. So to repel this as per Lenz's law, this loop too needs to develop a south polarity if you look at the loop from the side of the coil. So the loop from the side of the coil will develop, a south polarity to repel this south polarity. So since there has to be a south polarity on the loop, so from the side of the coil, the current has to flow in the clockwise direction. So again, look at the 3D concept. The dotted lines are extending from the center. So this means that the x is, if you look at, this means that the x is on the other side and z is towards you, x is away from you. Now look at the loop from the side of the coil. Since z is towards you, when you look at the loop from the side of the coil, z comes on the right hand side. So I draw the loop on the plane of the paper. With the z on the right hand side, and since the loop develops a south polarity, we draw the current direction. We put an arrow here to show that the current is moving in the clockwise direction. So we look at another problem here where the current carrying coil and a loop here, with the current carrying coil and a loop here. The current carrying coil is this time carrying current in the anti-clockwise direction. If you look at the coil from the side of the loop, the current is in the coil is in the anti-clockwise direction. Now, have you seen this? The current in the coil is in the anti-clockwise direction. We need to predict the direction of current in this loop. So if we look at the loop, since the current, coming back to the coil, since the current in the coil is in the anti-clockwise direction, it develops a north polarity. To oppose this north polarity, the polarity in the coil on the side in the loop on the side of the coil will also be north. So to oppose this north polarity of the coil, the loop on the side of the coil will also develop a north polarity. Hence, the loop should also carry current in the anti-clockwise direction when seen from the side of the coil. So if we look at the 3D way of looking at the coil, we see that from the side of we look at the loop from the side of the coil, we realize that X is on my left hand side and Z is on the right hand side. So since this loop should also develop north polarity, the current should be anti-clockwise, and hence the current in this should flow from Y, X, Z. We come and we look at a different problem here. The magnetic flux through the loop, increases according to this formula. So it's based on time. It's time based. So the flux increases as the time increases. Since this is a flux out, and this is a flux out, and there is going to be an increase in flux out with time. So there has to be flux induced to counter this. So to induce and flux, so flux in has to be induced. To induce flux in, we need to have a south polarity developed in this coil. So the current has to be in the clockwise direction. So through the resistance, the direction of current will be from right to left. We look at a different problem wherein we have the south pole of a bar magnet is moved towards this loop. This is mounted on an insulated material. We need to predict the direction of current in this loop. So as the south pole of the magnet is moved towards the loop facing the magnet should also develop south polarity, and hence the current should move in a clockwise direction if we look at the loop from the side of the magnet. In this case, this magnet is pushed through the loop to this side. So once the south pole is approaching the loop, if we look at the loop from the side of the magnet, the loop should develop a south polarity and the current should move in the clockwise direction. Once it crosses the loop and the north pole moves away from the loop, the coil should develop again a south pole on this side to attract the north pole of the magnet which is going away from the loop. So if you look at this side, look at the loop from this side, it again develops a south pole and the current is again clockwise if we look at the loop from the left hand side of the loop. We look at a different problem in which the south pole of the bar magnet is moved towards the loop. So we need to predict the direction of the current from this side. So what will be the direction of current if we look at the loop from this side? So since the south pole of the bar magnet is moved towards the loop, if we look at the loop from this side, it should develop a south polarity to repel the south pole of the magnet, and hence the current should move in the clockwise direction if we look at it from this side. Since there is a south pole on this side, there has to be a north polarity on this side, on the side of the eye, and hence the current on this side should be anti-clockwise. So the answer is, if we want to look at the direction of current from the side of the eye, the current direction is anti-clockwise. Now we have a bar magnet which is moved towards coil. This is moved towards solenoid 2. Since the south pole of the magnet is moved towards this, there has to be a south polarity on the side of the bar magnet, and the current on this wire should be clockwise, and hence the current through the resistance will be moving from C to D. Since the north pole of the magnet is going away from this solenoid, so this side of the solenoid should develop a south pole to attract the north pole. Hence, the current direction should be clockwise. Hence, the current should be on this arm should be in this direction. So, in the resistance, the current direction is from B to A. Hope you have understood the concepts of Lenz's law. In case of any doubts, you can contact me in www.olympiadtester.com. Thank you.